Hello, I'm Bill Walter. Welcome to the Block and Tackle Pulley System activity. In this video, we will explore block and tackle pulley systems and how they are used to lift heavy loads. The estimated time to complete the video and experiments is about 1 hour. You will need the following materials for this project: a broom or mop with shopping bag to cover the end, an 8 feet of 1/8 inch braided rope, 3D printed pulleys, clear tape, 2 small mouth plastic soda bottles or water bottles, liquid measuring cups and tap water, pen or pencil, and the block and tackle worksheet to record results. If you don't have the kit with the 3D printed pulleys, there's a link to the 3D print files in the description of the video below. Let's take a look at these materials. So the materials you'll need for the block and tackle experiment are a broom, a shopping bag to cover the end of the broom because we're going to place it on the table. You will need some water. I've got a bottle here, but you can get it from the sink. You'll need 2 small 16 to 20 ounce water or soda bottles. You'll need a 1 or 2 cup liquid measuring cup. You'll also need the 3D printed pulley pieces shown here, along with the rope. You'll need some clear tape, and you'll need the block and tackle worksheet and a pencil to fill out the worksheet. Pulleys are one of the 6 simple machines. A simple machine is a mechanical device that changes the direction or magnitude of a force. In general, simple machines use mechanical advantage to multiply force. The 6 simple machines are shown in the diagrams below. They include the inclined plane, a wedge, a lever, a wheel and axle, a screw, and of course, pulleys. A pulley, as shown in the left diagram, is a wheel with a grooved rim which acts to change the direction of force applied to a rope. Here we see a weight, which is pulling down, is getting lifted by a rope which is being pulled off to the side. Block and tackle is a mechanism consisting of rope and 1 or more pulley blocks which uses mechanical advantage to lift heavy objects. Mechanical advantage is a measure of the force amplification achieved by using a tool such as a block and tackle pulley. Pulleys have many uses and can be found in many everyday objects such as fishing poles, flag poles, engines, cranes, sailboats, and many more. Our first experiment will be a single pulley example. In this example, a single pulley is used to hold up the load, as shown in the diagram on the right. The load in our example will be a bottle filled with 16 ounces of water. The unused pulleys shown in this example will be used later to gain mechanical advantage. We are going to add a single pulley to our experiment to change the force direction. As you can see from the diagram, the load force pulls to the right while the pulling force pulls down. This pulley only changes the direction of the force. It does not improve mechanical advantage. Therefore, the load force equals the pulling force. To find where our system balances, a second bottle will be added as our controlled lifting force. We will change the amount of water in the second bottle to figure out where the system balances. Okay, let's set up our first experiment. Okay, first thing you want to do for your setup is to take your shopping bag and cover the end of the broom. This is so that you don't get whatever's on the broom on your table. And set it on the table. Make sure the broom handle hangs a little more than 1 foot off of the table. I have mine hanging about 14 inches to here. To keep the broom from falling off the table, you might want to take some heavy books and place them over the end of the broom. Now we're going to attach 2 of the pulleys. One of them has 2 with the T on the top, 2 pulleys with the T on the top, and the other one has a single pulley with a T on the top. So we're going to start with the small one, and you're going to want to use the clear tape. I'm going to use blue tape just so that you can see what I'm doing. But you're going to place the tape underneath the T's like so, and then we're going to attach it out near the end of our broom. And then make sure it's hanging straight down. Now we're going to do the same thing with the 2 pulley. So we got the tape on the 2 sides of the T, and we're going to place it about 1 inch from the table. You want to stay away if you've got some kind of a table cover. You don't want that to interfere with the experiment. But tape it up good like so, and again, make sure it's hanging straight down. Now we're going to fill our water bottles for the first experiment. But before we do that, let's prepare our plastic pieces. You'll notice there's a U-shaped piece and an O-shaped piece. You want to put one of the foot of the U-shaped piece inside the O, and then squeeze the other one in just so it goes inside. You'll find it makes a little basket. Do the same thing for the pulley. 1 foot in, squeeze the other one in so that it's held up. Okay, those are ready. Now, get your measuring cup, and it should say 8 ounces on it, or it should be listed in ounces. 8 ounces is equal to 1 cup. So you're going to take your water. I'm doing this over the table. You may want to do this over the sink so that you don't make a mess, but I'm going to be careful. I'm going to pour in exactly 8 ounces. So once you see that there's 8 ounces in there, take one of your empty bottles and carefully pour the water into the bottle. Try not to spill any, because you want exactly 8 ounces of water inside the bottle. Now do that one more time. Now you're going to have 16 ounces of water in your first bottle. Then take the first plastic piece, set it over the top of the open bottle, put the cap on, and screw it down. Now you'll see that the water bottle is held captive by the cap. We're going to do the exact same thing for the second bottle. We're going to fill it with 16 ounces. So start out by filling your cup to 8. And pour it into the second bottle. And one more time so that you have 16 ounces. If you spill some of the water, I recommend pouring the water out and starting over so that you can make sure that you have exactly 16 ounces in there. Again, put the plastic cap on and screw down the cap. And make sure it's held on tight. Alright, we're ready for our first experiment. So for the first experiment, we're going to take our water bottle with the pulley on the top and our rope. You want the end without the knot in it. You're going to put the rope through the little loop at the top and then pull it all the way through till the knot gets caught and it holds the bottle up. Now take the rope and feed it through the top pulley and through the second pulley, making sure that the rope rides in the groove of the pulley, like so. Now take the rope and feed it through the hole on the top of the plastic piece attached to the cap. Now we're going to lift these up until they're about in the middle, hanging in the middle, and then just take the rope and run it around back and through the loop like so, and just pull it, and you'll see it'll hold the bottle like so. Now if I let go of this bottle, we notice that they're balanced. That means that this bottle is pulling down with the same force that this bottle is pulling down. And if I set them in any other position, they will stay there because it's balanced. Okay, now to release the bottle, all you have to do is just pull on the limp end of the string, and then it will come right out. Okay. Let's go over to the table or the sink and remove 4 ounces of water from the bottle. Okay, so we want to remove 4 ounces of water from our 16-ounce bottle. So 16 minus 4 is 12. So after we remove 4 ounces of water, we'll have 12 ounces of water in the bottle. So take the cap off and the top plastic part and remove 4 ounces. 4 ounces of water is 1/2 cup. So very carefully pour out the 4 ounces. Then put the plastic basket and cap back on as we've done before. Keep the 4 ounces in the cup, measuring cup, because we'll come back to this. So now we have 12 ounces in this bottle and 16 ounces in this bottle. So let's do our same thing. We're going to put the string through the loop at the top of the bottle, lift the two up so they're about level. Take your string around the back and through the loop and pull it tight. Now, when I let go of this, what's going to happen? That one's heavier than this one, and so we see that that one falls because it's not balanced. So what did we learn from this experiment? For the single pulley example, the system balances when the lifting bottle weight is the same as the bottle load weight. Therefore, there is no mechanical advantage in a single pulley system. The pull force equals the load force. So let's get out our block and tackle worksheet and fill in the single pulley example. In this example, we found that the balance weight was 16 ounces and there was no mechanical advantage. We state this by saying 1:1, which means for every ounce of balance weight, you have 1 ounce of load. So therefore, there is no mechanical advantage. Your balance weight equals your load weight. All right, let's start working on the double pulley example. You might find it useful to use the diagram in your block and tackle worksheet to help set up the experiment. So now we're going to move on to our dual pulley example. In this example, there are 2 pulleys holding up the load bottle now, as seen in the picture at the right. Notice now that there are 2 ropes holding up the load bottle in the dual pulley example, where in our single pulley example, there was only 1. We'll talk more about this after our experiment. Let's move on to the experiment. Okay. So let's move on to the second part of the experiment. You need to completely remove the string from everything. Now put the string, the side without the knot, through the loop on this top pulley and pull it until the knot tightens. Now we're on to the second experiment, and we're going to put the rope through the top pulley connected to the bottle. And pull it all the way. Then we're going to go through the top pulley here and through the second pulley, making sure that the rope rides in the groove of the pulley. Now we're set up for the second experiment. Again, go through the hole. Let's lift it up so that they're both suspended. Tie our loop like we've been doing. Okay, so now we have a heavier one over there and a lighter one over here. When I let go of this, is the lighter one going to go up or is it going to go down? Stop here for a moment, make your guess, and then let's do the experiment and see what happens. So when I let go of the lighter one, it goes down. That means a lighter one is holding up a heavier one. So we need to reduce the weight in this to balance. So let's remove the knot. And let's go remove another 4 ounces from this bottle so that we have a total of 8 ounces in this bottle. Okay. We still have our 4 ounces that we poured out of the water bottle the last time. Take the lid off and pour out another 4 ounces so that we're at 8 ounces out of the bottle. So we had 16 ounces in the bottle. We just removed 8. That means we have 8 ounces left in the bottle. Put the cap and the plastic piece back on the bottle. And let's go back to the second experiment. So we now have 8 ounces in this bottle and 16 ounces in this bottle. Still in our second experiment setup. So again, thread the string through, lift them up so they're both suspended, tie off the bottle, and now when we let go, what do you think is going to happen? Take a moment and think about what's going to happen, and then we're going to try the experiment. If you need to stop the video, go ahead. Okay, I'm going to let go of the bottle now. Let's see what happens. They're balanced. We have 16 ounces over here and only 8 ounces over here. And yet, they're still balanced. I can put them at any level and they stay put. That means we have twice the water in this bottle than we do in this one. That is called a mechanical advantage of 2. We can suspend twice the weight as what is being pulled down. Let's look at how we got mechanical advantage from this system. Since the force on both sides of a pulley must balance, we see that the 2 rope segments holding up the load bottle must be equal, and their sum must equal the load. So each side is holding up 8 ounces as shown in the diagram at the right. As we learned in the first example, the top 2 pulleys just change the direction of the force, not the amount. So the lifting bottle only needs 8 ounces to support the 16-ounce load. This is a mechanical advantage of 2 because we can lift a load that is twice as heavy as what we're pulling. We can write mechanical advantage as lifting force to load force. In this example, we write 1:2 because we can lift twice the load as what we are pulling. So get out your block and tackle worksheet and let's fill in the double pulley example. In this example, we found that the balance weight was 8 ounces and the mechanical advantage is 1:2. Once you've finished filling out your worksheet, we'll get started on the third example. For our triple pulley example, we've added a third pulley to our load side as shown in the diagram to the right. Notice that now we have 3 ropes holding up the load as shown in the diagram. All right, let's start our experiment. Let's take this bottle off and we're going to get ready for experiment 3. Let's go remove some water from this bottle. Okay, we have our 8 ounces in the bottle and we had 8 ounces in the cup. What we're going to do is pour out the 8 ounces that we have in the cup. So you can just put that right back into the sink, down the drain. Not going to need it. And what we're going to do now is we're going to pour out 1/3 of a cup from the bottle. All right. And whenever you're measuring, make sure you leave the measuring cup on the table, because if you tip it, you're going to get the wrong result. So you want it to be flat on the table when you're measuring the result. Let's put our cap back on and keep the 1/3 cup inside the measuring cup, because we're going to come back to that. All right, let's go to our third experiment. Okay, now we're ready for the third experiment. We need to remove the string from all the pulleys. And from this pulley. And now we want to rethread the end without the knot back through the bottle at the top. All right. Now we're going to go up and put our string just above the lower pulley. And same thing on the bottom. We're going to go between the upper and the lower pulley. And then through the top of the top pulley and through the second pulley. And now we're going to latch it into the bottle. And again, lift them up so they're both suspended. And tie off the second bottle. Now, there's 16 ounces of water in this bottle and about 5.3 ounces of water in this bottle. What do you think is going to happen when I let go of the bottle? Will it balance, or will this bottle go up or down? Take a moment and take a guess, and then I'm going to let go of the bottle, or you can go do the experiment and find out for yourself. Okay, I'm going to let go of the bottle. Let's see what happens. They're balanced. Again, we have 16 ounces here and only 5.3 ounces here. I can put these at any level and it stays balanced. Since we know that the forces on all sides of the pulleys must balance, we see that the 3 rope segments holding up the load must be equal. And again, their sum must equal the total load. So each side is holding up 16 divided by 3 ounces, as shown in the diagram to the right. 16 divided by 3 is about 5.3 ounces, as we found in our experiment. Again, the top 2 pulleys just change the direction of the force, not the amount. So the lifting bottle only needed to provide 5.3 ounces to support the 16-ounce load bottle. We lift a load 3 times as heavy as what we pull. This is a mechanical advantage of 1 to 3. Let's get out your block and tackle worksheet and fill in the triple pulley example. Here we found the balance weight was 5.3 ounces and the mechanical advantage is 1:3. Take a moment to fill out your block and tackle worksheet and then we'll get on to our 4th example. For our final example, we're going to add a 4th pulley to our system. So we now have 4 pulleys suspending our load. Also notice that we now have 4 segments of rope holding up the load. The astute observer will start to see a trend here. Okay, let's move on to our 4th experiment. Okay, we've got our water bottle back here. We still have our measuring cup with 1/3 cup in it. We're going to take the cap off of the bottle and we're going to pour out till it gets to exactly 1/2 cup. That's going to be 4 ounces. All right. We're going to put our cap and plastic piece back on. Now let's talk about what we had. When we started measuring the last time, we had 8 ounces in the bottle. We now have 4 ounces in the measuring cup. So 8 minus 4 means there's 4 ounces still inside the bottle. So our bottle has 4 ounces. Let's go to our 4th experiment. Okay, now we have a bottle with only 4 ounces of water in it and another bottle with 16 ounces. Again, we have to undo all the pulleys because we need to set it up for the way we're going to do the 4th experiment. And this time the rope starts at the bottom of the upper pulley. Again, pull it until the knot catches. Now you want to go in between the 2 pulleys, so you're up against the top pulley, the small one. Go through the small one on the top. Now go through the large one at the bottom. And now through the large one at the top, through the second pulley, and now thread it through the water bottle. Oops. Oh, so here I got the string caught. So you got to make sure all of the strings go through the pulleys correctly, or it will catch like that. Alright, let's try that again. Let's pull them up so that they're both suspended. Tie off our bottle like we've been doing. And now again, take a moment to guess what happens when I let go of the bottle. Balanced, does it go up or down? And let's do the experiment. Alright, I'm going to let go of the bottle. And see, it balances. We have 16 ounces here, only 4 ounces of here. That means only 1/4 of the weight is needed to balance. As we learned in the previous 2 examples, the 4 rope segments holding up the load divide the load equally, or 16 divided by 4, which equals 4 ounces. So we only need 4 ounces on the lifting side to balance the 16-ounce load. This is a mechanical advantage of 4. Notice that the mechanical advantage is always equal to the number of pulleys or ropes suspending the load. So if we expanded this experiment to 8 load pulleys, we would only need 2 ounces on the lifting side to balance the 16-ounce load. So let's get out your block and tackle worksheet and fill in the quad pulley example. In this case, the balance weight was 4 ounces and the mechanical advantage was 1:4. This video has shown how pulleys can be used to gain mechanical advantage to lift heavy loads. I will leave you with one last experiment to do on your own. Set up each example again without the lifting bottle. Pull all the slack out of the rope until the load bottle is just about to lift off the floor. Now, grasp the lifting string exactly 12 inches up from the floor and pull it down to the floor. Now, measure how high the load bottle is off the floor. See if you can figure out a trend with the mechanical advantage like we did with the balancing weight. I really hope you enjoyed this video and learned something about the mechanical properties of pulleys. Thank you for watching.